Okay, so let me welcome you to this third lecture of our course on reinforcement learning. Today, we are going to continue our discussion on linear quadratic problems and our more general discussion of infinite horizon problems. And we are going to introduce an important conceptual framework that I alluded to in the first lecture, approximation in value space and its connection to Newton's method. We're going to use the linear quadratic problem as a vehicle for visualizations that will be important throughout our course. Then in the second half of the lecture, we're going to talk about examples of problem formulation and reformulation. So here's my outline. First, we're going to do an overview of our infinite horizon theory. Then we're going to apply this theory to linear quadratic problems. And then we're going to use visualization to look at things like the solution of Bellman's equation, approximation in value space, various forms of rollout, and so on. Then we're going to take a break. This number 2 part is going to be quite long. And we're going to take a break and then come back to discuss how we formulate dynamic programming problems and give some examples. One technique that's very common is state augmentation. Another reformulation is for multi-agent problems. We're going to discuss those now a little bit and more later. And then we're going to talk about partial state observation problems. So let's go to an overview of infinite horizon problems. And I have managed to put almost the entire theory, both analytical and algorithmic, on a single slide, thanks to abstract notation using Bellman operators. So here's the problem. We have a system that evolves according to an equation like so, where xk is the state, uk is the control, wk is a random quantity, a random disturbance, and the state evolves from xk to xk plus 1 according to this equation over an infinite number of stages. At the kth stage, there's a cost g that depends on state control and disturbance, and it's also discounted by a discount factor which could be equal to 1, in which case you have an undiscounted problem. And the important notation that we introduced last time, and it's going to be convenient for us both for visualization and also your class notes and books, textbooks for analysis, is that of a Bellman operator. There are 2 Bellman operators, the min Bellman operator T and the mu Bellman operator T mu that corresponds to a stationary policy mu. Mu here is a policy, maps states to controls. So T now maps functions J, functions of the state, into other functions, T sub J of the state, according to this equation. Now you'll recognize here this expression as the right-hand side of Bellman's equation and also of all kinds of dynamic programming expressions. It involves minimization over the first stage cost, the expected value of the first stage cost, plus the expected value of the cost to go from the next state that we land using u, and also as measured, as represented by the function j. So this j is like a cost function, and t sub j is another cost function that's obtained by the minimization that arises in dynamic programming kind of expressions. Now, the mu Bellman operator corresponds to a policy mu, is the same thing, except that instead of minimizing over all u, we use the u that corresponds to mu. We use mu sub x in place of u, and we focus on just a single policy. And now, with these 2 operators, it's possible to write the theory in the algorithm using the Bellman operators. J star, the optimal cost function, is a fixed point of t, satisfies this equation. You call this the min Bellman equation. Also, this equation characterizes optimal policies. In particular, if mu sub x attains the minimum in this expression, then the policy mu is optimal. And we represent this like so: T mu sub j star equal to T sub j star. There's another Bellman equation that corresponds to a policy mu. We call this the mu Bellman equation. And it says that the cost function of mu, which we denote by j mu, is a fixed point of T mu. Then we have the value iteration algorithm. It starts from some function j0, applies the min Bellman operator to it to obtain j1, then j2, and so on. And generally speaking, it converges to j star. There is also a value iteration algorithm that corresponds to a policy mu. It starts from a j0, generates j1, j2, and so on by applying the mu Bellman operator. And this sequence that's generated converges to j mu, generally speaking. And the policy iteration algorithm can also be described by using the T and T mu operators. Policy evaluation can be written like so. For a given policy mu k, it evaluates it by finding the fixed point of the corresponding mu Bellman operator. And then it improves it by applying T to it to obtain a new policy mu k plus 1. So it generates a sequence of policies, and the hope is that it converges to an optimal policy. So all the theory can be written in one slide by using T and T mu. And now what we're going to do is specialize these operators to the linear quadratic problem. So here we have a one-dimensional linear system. There's no disturbance. A and B are known scalars. Use the control one-dimensional. It's a real number. Xk is the state, again, a real number. And the cost function is undiscounted quadratic. There's a quadratic cost on control with R. R is a positive number, and there's a quadratic cost per stage for the state. Q is a positive number again, and we take the limit over an infinite number of stages. Okay, so this is the system equation. This is the quadratic cost per stage. And the min Bellman equation is obtained by the formula from the preceding slide. This is optimal cost to go from the next state. This is the cost per stage, and we minimize over U. And the nice thing to note here that if J star is quadratic, then this becomes a quadratic minimization in U and can be done in closed form. And as a result, the left-hand side, the result of this minimization, is also a quadratic function of X. This is the key to linear quadratic problems, a favorable quadratic minimization in the Bellman equation. For the linear policy, for multiplying the state, so for a scalar L, this defines a linear policy. The corresponding mu Bellman equation is given like so. So we plug Lx in here, and we obtain RL squared X squared and so on. So again, for a J mu that's quadratic, this expression here is also quadratic in X, and can be done in closed form. So here's the important fact, and we went through this last time. The Bellman equations admit quadratic solutions. J star, the optimal cost function, has this form where K star is some scalar. And for a linear policy, the corresponding cost is quadratic with some coefficient KL for a given L. And K star and KL solve the Riccati equations. Now here's the Riccati equation for the min operator, the one that's solved by K star. It involves this right-hand side, which is obtained from this minimization when we plug in K star, K, X squared here. And I denote this entire function of K by F of K. And we call this the Riccati operator. And the Riccati equation is K equals to F of K. Now, for a linear policy with L coefficient, there's a corresponding Riccati equation obtained from here. It has this form. FL of K is this function, and the corresponding coefficient KL is a solution to this L Riccati equation. Notice that this is linear in K, okay? Whereas this is quadratic in K, non-linear. This one is linear in K. That's not going to be an important fact in what follows. Now, if you minimize it here in the Bellman equation and you do all the calculations and you obtain the optimal policy as a linear function of L, there's an L star coefficient that characterizes the optimal policy. And from this minimization, it is obtained in this form with L star given by this formula here. Okay. Also, the value iteration algorithm is obtained by repeated applications of the Bellman operator or the Riccati operator by factoring out the x squared terms. If you start with a quadratic cost function, a quadratic initial condition for value iteration, you are going to obtain iterates that are quadratic of this form. And the sequence of this case is given by this formula here. This is, well, notice the resemblance here. It all comes out very easily from elementary calculations. So this is the basic theory of linear quadratic problems. And now we are going to try to visualize it. So we want to see how the min Riccati equation and the L Riccati equation are solved graphically. So here's the min Riccati equation. This is a faithful representation. It is concave, differentiable, approaches a horizontal asymptote on the right, and approaches a vertical asymptote on the left. And now the Riccati equation is K star equals F of K star. In other words, K star, the quadratic coefficient of the optimal cost function, is obtained as a fixed point of F. In other words, it is the point at which the red graph intercepts the 45-degree line. The red graph is F of K. The 45-degree line is K. And K star satisfies this equation. So that's the way to view the construction of the fixed point of F, the optimal solution of the optimal quadratic cost coefficient. Now, the L Riccati equation, remember, is linear. It has this form. For a given L, this is FLs of K, and the cost coefficient of the policy corresponding to L is obtained as the fixed point of this FL function, this linear function. The fixed point is this one here. This is KL. This is the cost function corresponding to a policy L sub x. Now, this picture depends on the slope of this green line. If the slope is less than 45 degrees, then there's a legitimate interception with a 45-degree line. You can see this from this expression. If A plus BL squared is less than 1, then the slope of the green line is less than 1. And A plus BL squared being less than 1 corresponds to a stable policy. Now, that's important to understand. When you plug in this policy corresponding to L into the linear system, then its trajectory can go down towards 0, or it can explode to infinity. And when it xk converges to 0, we say that the closed loop system is stable. And this corresponds to this coefficient here, which appears in the closed loop system being less than 1. On the other hand, if this is greater than 1, which corresponds to this case here, then the trajectory of the system explodes to infinity, and the cost is infinity. So even though this linear, line intersects the 45-degree line, the point of interception is unrelated to our problem. It does not give you the cost function of the policy. The cost function of the policy is infinity. So we are interested in graphs like this for stable policies, because the unstable policies give us bad stuff. Okay, so this is how we solve the min-Riccati and the L-Riccati equations. This one is linear, and for a stable policy, it does give you the cost of the policy. And this one is concave, and notice also that the green lines, all of them lie above the red line, because these are obtained by minimization. The red lines obtained by minimization of policies, and which must have graphs line above. So we're going to see later that these green lines and also these purple lines envelop the red graph. Before we do that, let's look at the value iteration. Remember, value iteration involves the generation of functions. If you start with a quadratic function, you get a sequence of quadratic functions of this form. They involve the the Riccati operator. So value iteration in the space of quadratic functions operates like so. It generates a sequence of k scalars as follows. At the typical iteration, we have the current iterate case of k. Then we compute f's of k, which is kk plus 1. We go up here, and this is the level of kk plus 1. We project this on the 45-degree line and then reflect it down to the horizontal line to get kk plus 1 over here. So this is the value iteration. From this point, it goes up horizontally and down to take kk plus 1. At the next iteration, kk plus 2, which is this, and so on. So it generates a staircase sequence in this graph. And you can see here that it converges to k star. Or does it? Well, it depends on whether you start from the right starting point. If you start from the starting points that are from here to here, it does work. If you start from starting points that are on this side, it does not. It converges to this point. But we always start value iteration at positive numbers, so it will always work for this one-dimensional linear quadratic problem. Okay, so we have constructions of solutions of the Riccati equations. We have value iteration. And now let's try to visualize the min-Riccati operator as a lower envelope of the L-Riccati operators. Remember, all these blue lines that correspond to linear policies lie above the red line. And I claim that they go all the way down to touch the red curve. And you can see this from this calculation. The Ricciardi operator involves this minimization over all controls. You can break down this minimization into two parts. First, minimize with respect to all u for a given level L, and then minimize over all L. So if you plug in here with u equals to L sub x, then what you obtain is this expression. So you can express the right-hand side of the T operator as the minimum of the right-hand side of the mu operators, like so. So what does this say? First of all, in shorthand, f of k is equal to the minimum of f else of k. In other words, f of k is obtained as the minimum of all those here, and in particular, for some fixed value of k, let's say k tilde, to obtain f of k tilde, we have to go up this way and record the crossing points with the blue lines, and we obtain the minimum crossing point. So in other words, there's some linear, some L Ricciardi operator that just touches here, according to this equation. And moreover, this Ricciardi operator is tangent to the min Ricciardi operator, and it is tangent because this f is concave. Okay, so it cannot cross into, it cannot be tangent, it cannot cross into under the red curve because all of these because all of these blue lines lie above the red curve. So from k tilde, we can compute the tangent Ricciardi operator k tilde according to this expression. And this Ricciardi operator, this L tilde operator, is a linearization. It can be viewed as a linearization of the Ricciardi, of the min Ricciardi operator at this point. So by obtaining the corresponding, by doing this minimization at k tilde, we obtain a linearization. This will connect with approximation in value space and also with Newton's method. Okay, so now, since we're going to talk about Newton's method, let's review it. You have seen it at some times because it's part of calculus. Sometimes it's taught in high school. And you can, Newton's method is usually presented as a method for solving equations, nonlinear equations. Let's view it for the context of a fixed point problem. Let's apply to the solution of finding a fixed point of a generic function g, of a variable y. G stands for generic. Okay, so here is g, and its fixed point is this point here, the point where y star equals to g, so y star. And Newton's method works by solving linearized fixed point problems. At the starting point, it finds a linearization of the g operator at that point, then solves the linearized problem, the linearized fixed point problem, to obtain the new point y1, then linearize again, and so on. So here it is. At the current iterate, yk, the typical iterate, we linearize the problem by using a first-order Taylor series expansion of g. And here, this is the gradient of g. So we obtain a function of y that is linear, and it depends, of course, on yk. And then we solve the linearized fixed point problem to obtain yk plus 1. In other words, we obtain the point yk plus 1 that satisfies this equation. This is Newton's method. And you can see that it converges very fast. It has nice properties, particularly when the g function is concave, which it is, fortunately, in our case. Now, you may have seen the Newton's method for the case of solving equations. This is an equivalent method. You can convert a fixed point problem into a problem of finding a zero of the function h given by g minus y. And you can apply this method to this context, and it's a similar figure, except it's just rotated so that this line here becomes a horizontal. And this calculation is isomorphic. It's to this calculation here. They're the same calculations, we just represent it differently using the equation solution format versus the fixed point solution format. Okay, so this is Newton's method. It has extensions to the problems, to multidimensional problems, solving systems of nonlinear equations or multidimensional fixed point problems. And you have probably seen it for the case where this G is differentiable, okay? However, it admits also an extension to non-differentiable problems, which is important for our case because the Bellman operator is differentiable in the case of a linear quadratic problem, but it is non-differentiable in general. So here what's happening, here's how Newton's method works for solving non-differentiable equations. This theory, by the way, relates to the theory of non-smooth analysis, which is relatively recent applied math. It dates to, let's say, around 1980. It's about 40 years old. And people don't quite realize that Newton's method can solve non-differentiable problems. And the simplest case is when you have an h function that's the minimum of several other functions that are differentiable. So here we want to find a zero of this minimum. And you can see that here's h1, okay? Here is h2, and here is h3. And the minimum of all those is a non-differentiable function. How do you apply Newton's method for finding a zero, y star, of this non-differentiable function? Well, it's a similar rationale. We linearize the problem at the current iterate. So if we're here, we linearize like so. If we're here, we linearize like so. We use linearization by a first-order Taylor series expansion of any one of the active components of h at yk. The h's that attain the minimum here. So the active components here in this region is h1. The active component in this region is h2, h3, and so on. At the corner points, both of these are active components, and we choose any one of them to linearize. And similarly here. Once we choose a component that is active at the current iterate, we solve the linearized problem involving just that component, and we obtain yk plus 1. So we are here, we linearize the corresponding active component and obtain y1. Then we linearize a different component, whichever is active. And if we had a corner, if we are over here, we could choose any one of the two components, any one of the components that are active. And it's not difficult to see in this simplified picture that the method works fine. Newton's method works for this function here, works for this function here alone, and so y1 is going to be closer to y star than y0, assuming, of course, that Newton's method works for this function. The important thing is that near the solution, we apply Newton's method for the active components at the solution, and all of these Newton iterations bring you closer to y star. So that takes a little bit of getting used to, but that's an important fact here, that Newton's method not only generalizes to multidimensional problems, but also generalized to non-differentiable problems, fixed point problems and equations, such as the Bellman equation in general. So this is the method for equations and can also be used for the fixed point problem, a fixed point problem of this form, where each one of these g's define an h function. Okay, are there any questions about Newton's method? Okay, so now we're going to go into something important, visualization of approximation in value space with one step look ahead, no rollout, just a cost function approximation, and then use that in Bellman's equation to obtain a policy. Okay, so I have drawn here the Riccardi equation. This is the look-ahead function, look-ahead cost approximation, J tilde, what we have called J tilde. It's a quadratic involving a K tilde quadratic coefficient. And what we do here is we minimize in Bellman's equation with the J tilde used as cost function approximation, and we obtain the one-step look-ahead policy without rollout, just one-step look-ahead policy. Now, for linear quadratic problems, this is just the tangent Riccardi operator at K tilde. It is this F tilde given by this formula that attains the minimum here, and it is this tangent blue line. And what is the cost function associated with this L tilde policy? Well, we've solved the fixed point problem corresponding to this FL tilde. And this is the quadratic cost coefficient of the one-step look-ahead policy. The one-step look-ahead policy is L tilde, and its cost function is J mu tilde sub x. It's a quadratic function with this K L tilde coefficient. So we start with cost approximation like this, and by approximation in value space and one step look ahead, we end up with a policy that has this cost function. But now if we look at this figure and look back to Newton's method, this is exactly a Newton step, starting from this point. So the cost function of the look-ahead policy is obtained by a Newton step, starting from the cost function approximation that you have obtained, likely by offline training, and this is the online play policy that you have obtained. So that's a very basic picture connecting approximation in value space with the Newton step. Now, this corresponds to the simple case of one step look ahead, but no rollout. Suppose you had two-step look ahead and again, no rollout. So you start with a cost function approximation like this. Two-step look ahead means that we do one step look ahead on the result of another one step look ahead minimization. Now, one step look ahead minimization is a value iteration. So you start from K tilde, do a value iteration, you go up here, and you use this to do the linearization and solution of the corresponding linearization, minimization, and obtain a two-step look-ahead policy. Starting from K tilde, this is the result of the cost of the resulting two-step look-ahead policy. And in the case of multi-step look-ahead, we simply have more value iterations leading up to the start of the Newton step. And the longer the look-ahead, the better, because with value iteration, we tend to converge to K star, and Newton's method works better if we started. The Newton step works better if we started close to K star. So this is a little bit more complicated picture, which factors the effect of multi-step look-ahead. And now let's look at an important issue for control theories, but also in general, the issue of stability of the one-step look-ahead policy. Okay, so we can start with a cost function approximation k tilde to the right of k star. And then the policy that we're going to obtain is this, this tangent policy, which is stable. We're going to obtain an unstable tangent policy if we start to the left of this threshold point, where the slope is equal to 1. Everything to the right of this threshold gives you a stable policy. So we call this the region of stability. And it also happens to be the region of attraction of Newton's method, the set of starting points for which the Newton's method works. So when doing one-step look ahead, it is important to pick the cost function approximation in the right regions so that we obtain a policy that's stable or has a finite cost. However, if we are careless and we pick k tilde in the region of instability, then the policy that we obtain is a legitimate policy, but has infinite cost in this particular case of the linear quadratic problem. And there's a corresponding extension of conceptual extension to the more general problem. So this is the issue of stability and the issue of choosing properly the cost function approximation k tilde. Okay, so now let's go into rollout. Rollout is simply one-step look ahead, starting with the cost of the policy, of the base policy. So here's a picture. We have a stable policy mu, which is linear, and it has a Riccati operator, which is linear. The cost of that policy, J mu, is this point here, is the fixed point of the corresponding Riccati operator. And Newton's method linearizes at this point and gives you a look-ahead policy, which is what we call the rollout policy, that has cost function that is called J mu tilde. It has a linear cost coefficient L tilde, and it has a cost function which is at the end of this Newton step. So rollout with a stable linear base policy is just a Newton step from J mu to J mu tilde. And it brings you closer to K star than the base policy, and also a lot closer, because Newton's method has very fast convergence. And if you start close to, the closer you start, if you start close, you get much closer to K star. It has a quadratic convergence rate. But in general, particularly since the base policy cost lies on the right of K star, the initial improvement tends to be very big. This is consistent with what you observe in practice. One step of rollout can give you a very big improvement. And it's due to the fact that it involves a Newton step, and also the starting point of the Newton step is in the good region, the region of stability, and also on the flatter region of the Bellman operator or the Riccati operator. Okay, so now let's look at a more difficult picture. Let's look at the truncated rollout with some base policy, but we use only m value iteration steps rather than infinite number of value iterations, starting from some k tilde. So we have this linear base policy, and it has a linear graph like so. Its cost function is given as a quadratic function involving this quadratic cost coefficient. And we start at some k tilde, and we do rollout with m steps using this linear policy. This corresponds to value iteration. It's going to bring us somewhere here, somewhere closer to this point. Depending on where we start, we may going to be making different progress. We may start from the right or from the left. Now, when we do the truncated rollout step, we start the Newton step from the end of the value iterations. In other words, these value iterations with mu enhance the starting point, so to bring it closer to the quadratic cost coefficient, the corresponding quadratic cost coefficient, and then we do the Newton step to obtain the cost of the truncated rollout policy. So truncated rollout operates similar to multi-step look ahead. It just looks ahead with the rollout with the base policy, as opposed to using the Riccati operator. It uses the some L tilde Riccati operator. Okay, there's an interesting question. How many steps should I do? Do I do well with many steps or fewer steps? Should I try for more steps? And also more steps cost more computation. So this is something to think about, and we will consider it a little later. So now let's look at policy iteration for the linear quadratic problem. Policy iteration is just repeated rollout. You start with a base policy mu0, and which is linear and stable, and then you obtain another linear policy mu1, and then another by rollout, and then another linear policy L2 mu2 that is obtained by rollout on the preceding policy, and so on. So it starts with a linear policy mu0 with a linear cost coefficient, and generates a sequence of linear policies by rollout. And now one thing that I want to note here is that for rollout, if you start with a stable policy, you end up also with a stable policy. So by repeated rollout, you obtain a sequence of stable policies. And the calculations for doing the policy evaluation are given here. We have gone through these formulas before. The mu k has a cost coefficient case of k, which is given by this expression. And the policy improvement is obtained by minimizing in the Riccati equation with k equals to kk, and gives you lk plus 1, another linear policy, and its coefficient is given by this expression. And rollout is just a single Newton iteration. Policy iteration is a full-fledged Newton's method, an infinite number of Newton iterations for solving the Riccati equation. There are also some variants of policy iteration. The one is called optimistic policy iteration, where instead of using a rollout, we use truncated rollout. And basically, this amounts to policy evaluation by value iteration, by a finite number of value iterations. And it can also be viewed as a Newton step. There's always a Newton step at the end, and the preceding value iterations define the starting point of the Newton step. And in the parlance of numerical analysis, this is called a Newton SOR method, which is a mixture of a Newton iteration with first order iterations. SOR stands for successive over-relaxation. It's a legitimate method that has quite a bit of literature and has seen a lot of practice. We're going to get to optimistic policy iteration later, just to make you aware that there are variants of policy iteration, and one of them is this optimistic, and there are other variants that we're going to encounter. Okay, are there any questions so far?
Professor?
Yes.
So how many of these results would hold if the function curve for the, what is the word? Yeah, the minimum Riccati equation, if that function was not concave?
If it was not concave, then all sorts of anomalies can happen. For example, the Newton's method would work, but the region of convergence of Newton's method would be a lot different than it is here. Here, the region of convergence of Newton's method is defined by a certain threshold, and it's the right-hand side of the real line on the right of that threshold. If you had a Riccati equation that were a mixture of convex and concave segments, this would not be true. So, however, in dynamic programming, the Bellman equation is concave, always. So we have that benefit, concave and monotone. The Bellman operator is concave and monotone. This is something that helps a great deal.
Oh, okay, I didn't know that. Okay, sorry, yeah.
Yes.
Thanks.
What I should have mentioned here is that even though we look at these pictures for the linear quadratic problem, and in fact, the one-dimensional linear quadratic problem, because otherwise we would not be able to do visualization because there's one equation for every state. So if we were to look at a two-state problem, in general, it would be difficult. And here we're looking in the case of linear quadratic problems, we look at Bellman's equation within a subspace of quadratic functions. So we're looking at a special case. However, the nice thing is that the insights that we obtain from the special case carry out in great generality for arbitrary dynamic programming problems with a single optimizer, not two-person players, but for a single player. And regardless of the state space can be discrete, a finite number of states, or it could be continuous, like a Euclidean space. What is important is that the Bellman equation is always on a function space. It's not affected by, it's just a matter of whether the Bellman equation is multidimensional or finite dimensional or infinite dimensional. The insights carry through. Everything I'm discussing today for the linear quadratic problem has analogs and that for the more general case, and the insights are very similar. That's the nice thing about this linear quadratic problems. It's really a good friend in our context. So let's take a 15-minute break, and you can collect your questions. And here's a question for you to think about. How long should the length of the truncated rollout be? And issues of performance stability of the Lookahead policy in in conjunction with how long the truncated rollout is. The picture that's relevant here is this picture here that I showed you earlier. And I'd like you to look at this picture with this question in mind. How long should be the length of the truncated rollout, and how does it affect performance of the look-ahead policy, and how does it affect stability? So let's break now for 15 minutes, and we will come back at 7:41 Arizona time. Okay, so we are ready to start. Are there any questions?
Hey, Professor, I have a question here.
Yeah.
What's the difference between truncated rollout and multi-step look-ahead?
In multi-step look-ahead minimization, you do the minimization. You minimize over all possible sequences or all possible controls. Whereas with rollout, at each stage you don't have a choice. You use the control specified by the policy, the base policy that you're using. So rollout with a policy is much cheaper than look-ahead minimization. It's a much cheaper computation.
Using the multi-city agent example, what is the multi-step look-ahead procedure?
Using what example? I'm sorry.
The multi-city travel agent. The travel agent.
The homework, you mean? The homework problem.
Yeah. Not necessarily that problem, but in that concept. What is the multi-step look-ahead for?
There's no multi-step look-ahead in that problem. It's all one-step look-ahead. One-step look-ahead minimization, and then the base policy. If we were to optimize over all trees of two-city choices or multi-city choices, and then use the base heuristic, then that would be an example of multi-step look-ahead minimization. But the minimization over multi-step, multiple steps, multiple cities is much more difficult than minimization over one city, over the next neighbor.
Okay. Thank you, Professor.
Okay. Any other questions? So briefly, let's look into this issue here. We have interpreted truncated rollout with M value derivations using the base policy, using this figure. And we start from some initial condition, K tilde, for the value iterations with mu. And we execute these iterations here, 1, 2, 3, 4. And then we obtain some point here, which is the cost approximation that's given to the one-step look ahead. It's a Newton step, and it takes us from here to here. So we started from here with all this truncated rollout. We got to this point, and we ended up at this point through the Newton step. Now, if we were to use untruncated rollout, we would start from here and then do a Newton step. However, in this way, with the value iterations, we have avoided the evaluation of K L tilde. We've done it through this, approximately through this value iterations. But the question arises, where should you pick K tilde, and how many steps of rollout would be good to use? So what do you think about that? Should I choose K tilde over here? Would it help me? And how many steps should I use? What is the number of steps that to use? If I pick it in this region here. Well, generally speaking, the answer is I should use as many steps as they bring me closer. They improve the starting point and they bring me closer to K star. So if I start somewhere over here, K tilde is over here, and do Newton steps and do the value iteration steps, that will take me close to this point here. It will not cross over to this side, it will just converge. As m goes to infinity, I would converge to this point here. So the more value iterations I do, the better off I am. Now, how about if I start right in here in this interval between K star and KL tilde and do value iterations? Okay, value iterations would move me towards KL tilde, right? It moved this way. Does it help me? Well, it doesn't help me because if I start anywhere in here and I do value iterations, they are going to push me towards more unfavorable starting point for the Newton step. On the other hand, it's not so big a deal because the Newton step is very powerful and don't lose all that much. What if I start to the left of K star? K tilde is like it is in this picture, to the left of K star. How many steps of value iteration steps should I use? Well, if I choose an infinite number of value iterations, then I'm going to converge to KL tilde. So there is some point that I will cross into this region here, and extra value iterations do not help me, actually take me further away from K star. So the answer is that I should use a fairly large number of value iteration steps, but after a certain point, they don't help me very much, or they don't help me. But the damage is relatively small again. There's one consideration, extra consideration here. Suppose that you have a stable base policy and K tilde is in the region of instability. In other words, if you were not going to do any rollout, you would get an unstable policy. Then you're in bad shape then, it's a problem. And the value iteration steps have the advantage that they push you towards the right, towards KL tilde, so they push you into the region of stability. So in this case, the truncated rollout not only improves the starting point for the Newton step, but also enhances the stability of the look-ahead policy. It's more likely that you will get a stable look-ahead policy if you choose a large number of value iteration steps. Okay, that's a little complicated. The figure itself is very complicated, but it's worth studying it after you have understood the mechanics of these figures. But are there any questions? Okay.
Professor, I have a question.
Yes.
So in the value iteration, you mentioned like at some point we cross the optimal point and we go ahead and we use some extra computation that does not help us.
Yes.
But
Yeah,
what makes the Newton step to come back to the optimal cost?
The Newton step is not like value iteration. The Newton step works much faster than value iteration, and also the Newton step is a different algorithm. It works within the region of stability, within the region of convergence of the method, and it is it is not it will go towards K star under as long as we are within the region of stability. So that's what helps Newton step. Newton step works very fast, very well from a large region. Now, when I said that many value iterations will not help that doesn't mean that the method will not work. They will simply push us to a more unfavorable starting point for the Newton step. And that's the point I want to make. That if I take M to be very large, I may get somewhat worse results than I would with a relatively small value of M. Of course, knowing the right value of M is not easy in given situations, but in some cases it can be obtained through some experimental computation, some preliminary experimental computation. It's good to understand, though, what is the role of the length of the rollout in terms of this figure.
All right, Professor. Thank you.
Okay.
Professor?
Okay. Yes.
Sorry. And also, in general, there's no way for us to know what K star is right off the bat. And so, in that sense, there's no real way to get a good estimate of an initialization value for K, right? Like the K tilde value. At the end of the day, there's no real way to know where to, like, what is a good guess to start from, right?
That's a good question. But there are ways to select good values for K tilde.
Oh.
One way is to start from an arbitrary K tilde and then use a stable policy. Assuming you know a stable policy, you can do a lot of value iterations to push it into the good values area. That's one way.
Oh, okay.
And the other is to simply use as initialization the cost function of some base policy. Okay, if I start the Newton step from here, it will work. It's because the region of stability includes all of these points that includes this entire region. Starting from a base policy that is stable is a good initialization. The only thing is that it costs you a lot to evaluate the rollout to use a stable policy to evaluate a rollout policy, to evaluate it and use it to generate the rollout policy. So there's always these regions here that can be this region and these values that correspond to stable policies that are good starting points for approximation in value space, as well as some points over here which can be improved with this value iterations. So there's a pretty good, one can have a pretty good handle on how you start the Newton step.
I see. Okay, yeah, thanks. Makes sense.
Okay, so before we go into the second half of this lecture, I want to give a summary figure of approximation in value space as a Newton step. And this is for linear quadratic problems. And this figure shows the two-step look-ahead minimization case. Two-step look-ahead minimization followed by truncated rollout, and then a cost function approximation that involves some K tilde coefficient. Okay, now this relates to the very first figure that I gave in this class of alpha zero. Alpha zero and related designs, related schemes involve at the current state a multi-step look-ahead minimization, possibly truncated rollout and cost function approximation at the end. And the online play algorithm is the one in blue here, and it uses the results of offline training at two steps to obtain the terminal cost function approximation, which is quadratic in this linear quadratic case, and to obtain a policy to roll out in the middle, assuming that there is truncated rollout in the scheme. Now, Newton step starts from here and involves just the first look-ahead minimization step. All the rest up to this point are value iterations of one form or another to enhance the starting point of the Newton step. If you consider the case of one step look ahead with cost function approximation, just one step look ahead minimization, and no rollout, then this entire part goes away. We have one step look ahead minimization with a terminal cost approximation, and this is a pure Newton step for solving the Bellman equation or the Riccati equation in our case. If you have two-step look ahead without any rollout, then this middle part is just this extra step of look ahead. If you add rollout to it, then there is this other value iterations that involve the base policy, the linear stable policy. And all of these parts can be designed in different ways. And all of this is part of online play. And offline training comes only at this parts here. Now, the Newton step is the one that does most of the work. It is the one that gives you the large cost improvement. It is an exact Newton step, whereas these parts may involve approximations. If there are approximations in here, either due to offline training or you get an approximate policy that's not very good, then this will affect the quality of the starting point, but the Newton step has the power to correct a lot of the mistakes that you may make in this part of the process. So that's a point that I want to make, and particularly since even though we have presented, we have given justification for the linear quadratic case, actually this figure and the corresponding insights go through in general, very generally. Finite state space, discrete optimization problems, infinite state space, stochastic problems, deterministic problems, anything goes. The figure stays the same and the insight stays the same. That's the important point that I want to impress on you. Now, of course, I still have to justify this very broad statement, but as we go along, we will see that there are justifications. And if you think through it, you'll find that actually this is a very general figure with a first Newton step and then enhancements to the Newton step, to enhancements to the starting point of the Newton step through extra look ahead minimization and also truncated rollout. Are there any questions about this figure?
Professor, I have a question here. Regarding the Newton step, my understanding is it will only point you to a new point. But in the figure, I see a fork out of the starting point. I'm wondering why the Newton method would give me two states. To me, the two states are more like a rollout. That's why I'm confused. In other words,
I don't know what you mean two states. I don't understand what you mean by the Newton step will give you two states. What do you mean? In this case, it's two-step look ahead. Okay, so you're looking at the next stage and then the stage 2 steps after. Is that what you mean?
I'm talking about the Newton step, like the bidirectional arrow, right? That the zone for Newton step at the bottom. On your diagram, you said Newton step for Bellman equation, right? In your diagram. So
Here?
my question, yeah, right here, exactly. So I'm confused because in my mind, a Newton step would only move from one state to the next state. It's point to point. But in the diagram, I see a fork. From
No, it doesn't
XK.
move from one state to another state. It moves from one function to another function. Okay, here, there are no states here, okay, in this figure. We represent cost functions. And in this particular case, because it's a linear quadratic problem, the cost functions are quadratic. So it's 1K for all states. So this is a cost function that we're plotting on the horizontal. And from one cost function, the cost function approximation, K tilde, we go into another cost function, which is the cost function of the one-step look-ahead policy. So we move from function to function with this Newton step. And the idea is that because Newton's method is very powerful because quadratic convergence, this step brings us very close to K star. Has very fast convergence rate. Okay, I think you should take a look at this figure and try to understand it a little better.
Okay, thanks, Professor.
Okay. Okay, coming back to this figure. If there are no questions, are there any questions? Okay, so now let's go into problem formulations. Practical problems, how do we formulate them as dynamic programming problems? In practice, you're not given dynamic programming problems, you're given a practical application. And I said earlier that dynamic programming is very powerful in terms of its range. It applies to just about any optimization problem that you can think of. But how do you make the formulation from some nebulous application into a mathematical problem where you have states, controls, stages, and so on? There's no one way to do it. I can only tell you how I do it. My recipe. I first define the controls because these are easy to define. In a given practical situation, you know what kind of means you have to affect what your decisions are. You also pretty much know when you apply your decisions and the information that's available with every decision. So that helps you to define the stages of the problem. And then the hardest part after you define controls and stages is what do you pick as states? And there is a reliable recipe here. You define a state a summary of all the relevant information, something that summarizes the past for the purposes of future optimization. In other words, a state should have some kind of a Markov property, whereby if you know its value, then it separates past from future. Whatever past information you receive, whatever happened in the past is not relevant for the purposes of future optimization. And the rationale for this is that the controller applies action that depends on the state. So we should include in the state all the information that's useful. And that's something that makes sense. It's also a reliable guideline. On the other hand, there are many different summaries that can serve this purpose. They have equivalent information, but they are different. So which one do you choose? For example, in the traveling salesman problem that we formulated as a dynamic programming problem, the state that we took was the collection of the cities that we have visited so far, the partial tour that we're in. Now, there may be additional information, such, for example, the cost incurred so far, but that's not relevant, and we need not include it in the state. This is only what's relevant. We could add additional information, but it may not be relevant, it may not be useful, and we don't want to add information that's not really useful because that increases our state space and makes the dynamic programming algorithm more difficult. Now, there is a class of problems called partial or imperfect state information, where we have something that we would like to call state. The only problem is that we don't know it exactly, so we cannot base control on its knowledge. Instead, we may have measurements of some quantity of interest, like what we would like to call state, which evolves over time. And we collect these measurements and we can use them to estimate a quantity of difference. For example, we may be interested in controlling a moving object, and the state may be that you would like to know is the position and velocity vector of that moving object. On the other hand, you may have only radar measurements that are noisy measurements of position and not velocity. So that's a situation where you have partial state information. Now, what do you pick as states in this context? Well, the state is something that summarizes all the past information that's useful for purposes of future optimization. So the entire collection of all the measurements that you have received up to time k is a legitimate state. It's correct to use that and write a corresponding dynamic programming formulation where the state is the state of information, so to speak. And it evolves over time with the addition of new measurements, and you can use it to apply controls. However, there are also alternative states, alternative possibilities of state choice that contain the same amount of information. One such possibility is a probabilistic state, so to speak, the conditional probability of the quantity of interest, yk, given the information we have obtained so far. So we would like to know yk, but we don't know it. We get measurements about it, and with an estimator, we can estimate the probability distribution of yk. Now, this is also, it turns out, a legitimate state. It's called belief state. This conditional probability distributions are called beliefs, and using this as state is called, it's like using belief states. And it turns out, with some proof that we're not going to give here, that it subsumes all the information that's useful for the purposes of control choice. So now I'm going to give some other examples of problem formulations, including the choice of state. And let's start with a technique called state augmentation. That's very useful. One example is when the system equation does not involve just the current state and the current control, but they may involve delayed states and delayed controls. So the next state may depend not only on xk, but on xk minus 1, xk minus 2, perhaps, uk minus 1, and so on. So that doesn't fit our framework. So what do we do? Well, we introduce additional state variables. Let's call them yk and sk, where yk is the delayed state and sk is the delayed control. And then we can write an expanded system equation where the state is augmented to include yk and sk, and the augmented state at time k plus 1 evolves according to this equation. Okay, remember, yk is xk minus 1, yk plus 1 is xk, and so on. So this is a correct equation. And now we can define as augmented state xk together with yk and sk. And then if we call this overall function f tilde, okay, then the new augmented state evolves as a function of the previous augmented state, the control, and wk. So we can get into a framework and we can write a dynamic programming algorithm for this augmented state problem. We start from the terminal cost function, and then we have a optimal cost to go calculation that involves not only the current state, but also the additional artificial states that we have introduced, a bigger state space over to execute this minimization that involves xk minus 1, uk minus 1 here. And when you take the expected value and then the minimization over uk, gives you a function of xk, xk minus 1, and uk minus 1. And then at the last stage, at state 0, then we don't need to include the delayed state and control. It takes the usual form that looks like this. So it's possible to do it, but the size of the state space has increased, and so have the computations of the dynamic programming algorithm. And this is generally true with this state augmentation technique. It can model just about everything. You just introduce additional state variables according to the rationale of what is useful information to know at the current time. However, state augmentation can increase the amount of computation that you have to do in the dynamic programming algorithm, and it can also complicate approximate dynamic programming algorithm techniques and reinforcement learning techniques. Sometimes reinforcement learning is very useful in simplifying this the consequences, simplifying this dynamic programming algorithm so that you keep the size of the state space relatively small. So we are going to be revisiting state augmentation techniques as we go along. And your class notes contain quite a few examples of state augmentation, including the case where you have forecasts of future uncertainty. Like this WK does not have a fixed probability distribution, but it may be changing depending on forecasts that you receive during the process of control. You can deal with such situations with state augmentation. And there are examples like this in your notes. You may look at them. Okay, let's look at another reformulation where you have a cost-free and absorbing terminal state. Basically, where the problem of the process of control stops at some state and there's no more cost to be incurred. An example of this type of situation is in games, where you lose the game or you win the game and it stops. You don't have to make any more decisions, and there is no further cost to be incurred. Generally speaking, problems with a termination state, you can view them as infinite horizon problems because you don't really know what the horizon is. You may not know how many steps it's going to take you to terminate. So you view them as infinite horizon problems, and you introduce this absorbing terminal state as part of your state space, and you encode all of this within the infinite horizon context. Now, there's another possibility that's useful that's often useful, is to convert the infinite horizon problem that involves the termination state into a finite horizon problem by introducing as horizon an upper bound to the optimal number of stages, assuming that you know such a bound, and then add a big penalty for not terminating before the end of the horizon, and that will provide an incentive to terminate within the finite horizon problem, and no loss of optimality is incurred. Here's an example. This is a multi-vehicle routing example where you have a number of vehicles that move within a graph, let's say a road network if you'd like, and they want to execute some tasks collectively. The tasks are what you see here with the dollar signs, and there are several of those tasks, and once a task is completed, then you don't have to do it anymore. A task is addressed only once. So so after all the tasks are done, you reach a termination state. On the other hand, how can we convert it to a finite horizon problem? There are policies, not very intelligent, that can execute for an infinite amount of time. For example, let's take a vehicle that goes back and forth between 2 and 5 here forever and ever, okay? And similarly, there are policies for other vehicles that just go around aimlessly, and there's no way you can bound the number of stages needed for policies like that. On the other hand, for an optimal policy, you can easily, within this context, estimate the number of moves that are necessary to execute all the tasks. So if we want to minimize the number of moves to perform all the tasks here to reach the termination state, we can provide an estimate of an upper bound of the number of moves needed. Now, here's another question. What do we pick as states in this problem? Let's take the problem is deterministic, and there are a number of vehicles located at different positions within this graph, and there are also a number of tasks located at different points. And let's assume that the tasks are deterministic. In other words, they don't change. There are no new tasks that are created, or all tasks that are eliminated by chance. Still, it's a very difficult problem. As part of the state, we ought to know the collective location of the vehicles. That's certainly useful information for future optimization. We also need to know how many tasks are located and as well as where they are. So that's also useful from the point of view of future optimization in moving the vehicles around. So very quickly, the number of states becomes astronomical. It's exponential in the number of vehicles, exponential in the number of tasks. How about controls? Well, the natural controls here are the joint moves of the vehicles. So one choice, for example, in this situation is for vehicle 2 to go here, for vehicle 1 to go here. And another possibility is for this vehicle to go here and this vehicle to go here. All the possible combinations of joint moves of the vehicles are legitimate controls in this setting, it would seem. On the other hand, the number of joint moves of the vehicles is also grows exponentially with the number of vehicles. And so it's a real problem. Even if you want to do rollout, the size of the control space is astronomical. It turns out that there's a general category of problems which we call multi-agent and include this problem, and they alleviate the difficulty with a large control size. So let's look at multi-agent problems. Okay, it's a very old class of problems. When I was a PhD student, they were still around. In fact, I worked on these problems when I was a PhD student until I realized how hard they were, and I gave up and went into a different topic. These problems involve multiple decision centers called agents. And each agent has a decision to make at each time period. So the collective control of all the agents is what you see here. It consists of m components, one component per agent. Now, these agents collect information from the environment. They share information among themselves selectively. Some agents may communicate with some agents, but not with other agents. And then after collecting this information, at the beginning of each stage, each agent applies a decision, and then it collects some more information up to the next decision, and so on. All of this happens in discrete time, either over a finite or over an infinite horizon. Now, one important characteristic of this situation is that the control consists of multiple components. So even if each U can take only a small number of values, if M is large, the search space, the control space can be very large. There's another interesting characteristic here is whether the agents have the same information or whether they act with different information. The case where the agents share the same information and also are fully cooperative is called the classical information pattern. They fully share information, they cooperate, and they never forget information. And this is a quote-unquote tractable problem because it can be treated by dynamic programming. It's just a special type of dynamic programming problem that has this type of structure. You can view all of these agents are being one because they share information and they cooperate. A much harder case is the non-classical information pattern, where the agents do not share the same information. They may share some information, but not all of it, and also possibly may be antagonistic. These problems are very hard, extremely hard. The main reason is that they cannot be treated by dynamic programming. For example, there's a class of problems called non-cooperative games, like Nash games. There's no dynamic programming algorithm for that context, even though there may be sequential decisions, choices of control, and so on. There is no starting point with dynamic programming that can serve also as an entry point towards reinforcement learning techniques that are out of the approximate dynamic programming type. Now, we're going to focus for the moment on this classical information pattern, and I can show you how you can reformulate them in a way that approximation techniques like rollout are easier to apply. So let's take the classical information pattern. We're going to deal with the non-classical information pattern later in quite a few lectures into the future. And because of the sharing of information, you can view it in terms of this picture. So at each time period, the agents have exact information, state information, and they choose their controls as function of the state. And this state is collected in some kind of a cloud, a sensor cloud, which sends back conceptually this information to all the agents. Now, the mathematical model for this is still a discrete time system with state X and control U, but the control has multiple components corresponding to the M agents. And I should point out also that agents is just a metaphor here. It may be that the agents are spread all over a geographical area, like the multiple vehicles of the problem I talked about earlier. Or it may be that these agents reside within the same computer or within the same robot. One control may control the left hand, another one may control the right hand, another one may control the some joints, and so on. It's best to view this as mathematically as a multi-component control structure. And you can still use dynamic programming in view of this classical information pattern. However, it's possible to reformulate the problem so that the computations become faster. So we will first aim to deal with the exponential size of the search or control space. And later we'll come back to the non-classical information pattern and also the possibility of computing the agent controls in some distributed fashion. So let's deal with this question here in the context of an example. Okay, so this is a canonical example. It applies to vehicle routing, multi-robot maintenance, search and rescue problems, firefighting, and many others. To make it a little more interesting and generic, I'm going to formulate in terms of spiders and flies. So there are spiders and there are flies, and the objective of the spiders is to catch the flies. And in this figure here, there are 15 spiders. that move with perfect vision of where the other spiders are and where the flies are. They have perfect vision, and each one moves in 4 directions, up, down, right, left, and also can stay where it is. So it has, each spider at each time step has 5 choices. We assume that the flies are blind. They don't see at all the spiders, and they move randomly. So the objective here is for the spiders working as a team to catch all the flies in minimum time. So the optimal policy may be for this spiders here to move towards this fly, and for other spiders to move towards this fly, and so on, and to encircle it, and so on. You can imagine the character of the optimal policy. However, to compute the optimal policy by dynamic programming is just impossible. The reason is that at every time step, the control is the collection of joint moves of the spiders. And each one has 5 options, and there are 15 of them. So the number of possible joint moves is 5 to the 15. It's astronomical. Now, we are going to reformulate the problem so that the control space is much smaller. And altogether, it involves a polynomial number of choices, 75 instead of 5 to the 15. And still, with this reformulation, be able to apply rollout and have and maintain good properties, good performance guarantees for this rollout algorithm. And the idea is, instead of considering joint move decisions, to break down the control into a sequence of 1 spider at a time moves. So in this reformulation, instead of all the spiders choosing a move collectively, they choose moves in sequence. So let's say first this spider here makes a move, then another spider makes a move, having seen the move of the first spider. Then a third spider may choose a move, having seen the moves of the preceding 2 spiders. And so in this way, there's only 5 choices per step. So it's 5 choices 15 times. And now we're going to give a theoretical framework for this and also an algorithm. But let me give you also a reference of discussion and videos of these problems. There's a YouTube video here. So how can we pass from collective choice to sequential choice and still stay within the boundary of optimality?
Professor?
Yes.
Is this like one at a time sequential optimization, like some sort of Gauss-Seidel optimization? Or
yeah, it is related to the idea of Gauss-Seidel, yes. On the other hand, it's in the context of dynamic programming, and even though there's a conceptual connection, it's not quite the same.
Thank you.
Okay, so I'm going to reformulate my problem by making the control space simpler while complicating the state space. And this is an old idea that dates back 25 years. But incidentally, this idea stayed dormant for a long time. It's only recently that has come to the forefront and has become useful within an interesting context like this multi-agent problems. Now, a state of the problem, call it X, in a single stage goes to some other state by choice of all the controls, all the components. Let's break down the application of components one at a time, and we break up the stage into multiple stages, M stages, by unfolding the control action. So from this state, we choose just U1, the first component, and go to another state, which is X of U1. Remember, a state can be anything, right? Our formulation is very general. So that's certainly legitimate. Now, from this state, I choose a control U2, and you go to this state that involves both components. This is a deterministic transition, and I assume zero cost here in my reformulation. Then I choose U3, and after M-1 choices, from this state, I have gone to this complicated state, but with simpler choices of controls at zero cost. And here I choose the last control, UM, and that's when I make the random transition to the new state according to the system equation, and I also incur the random cost. So it's pretty evident that by breaking down the stage into a sequence of component stages with application of component controls in between, you obtain an equivalent problem. It's the same problem. And what's happened here is that the control space has been simplified at the expense of M-1 additional layers of states and corresponding cost functions. If you want to execute a dynamic programming algorithm with these expanded stages, then you would have to calculate tail subproblems for each one of those stages. And this becomes very complicated. On the other hand, if you want to do just rollout with a base policy, as opposed to doing computing an optimal policy, this complication with the more complicated state space does not matter, because rollout does not care about how complicated the state space is. It only cares about how complicated the control space is, because it has to choose at every state that it encounters online, it has to choose a control. So we can use rollout, whereby at a given state like that, we know the current state because they are the previous controls that we have applied, and we use a base policy to assume values for the future controls. That's what rollout does. And in this way, we can do calculations only one control component at a time. So that's what I'm saying here. The increase in size of the state space does not adversely affect rollout. Only one stage per stage is looked at during online play. And there's a huge complexity reduction because the one-step look-ahead branching factor is reduced from n to the m, where n is the number of possible choices for each component, from this exponential number to n times n. I choose between n choices in this step, n choices in this step, and so on, is m times n. So that's what I gain computationally by breaking down the problem within the context of rollout. The reduction in computation is very, very, very significant. Now, do I lose something? Okay, well, this is not some kind of imperfect rollout. It's legitimate rollout, but for a reformulated problem. So it is still covered by a Newton step and by the cost reduction properties of rollout. Everything that you can prove for this all controls at once rollout, you can also prove for the one control at a time rollout. It still has the Newton interpretation and the cost reduction property. In computational examples that we have done, and you can also see in reference papers and also in the video for the spiders and flies problem, and also for other problems involving multiple robots maintenance and repair, we find that really there's no difference between the all at once control choices and one at a time control choices in terms of performance. You still have the characteristic cost reduction property of rollout. So it's a very, very important reformulation and a good starting point for addressing multi-agent problems. Not only in the context of rollout, but also in other contexts as well. We're going to return to multi-agent problems in future lectures. Are there any questions?
I had a quick question. So outside the context of rollouts, if we don't have a good base policy, if you're doing like normal value iteration with some initialization over the value function, this reformulation would still be as hard as the original problem, right? Because you've only moved the complexity to the states. Could you hear me?
Yes, I can hear you.
Yeah.
It depends on whether you do a computation that involves all states. For example,
Okay.
rollout is one possibility, but you can also do approximation in value space.
Right.
With online play. Online play involves only the state where you're currently at. So for an n stage problem, it involves only n stages and n calculations. So as long as you can decompose the minimization involved in the Lookahead, in the value iteration, as long as you can decompose into components, you gain in terms of computation. Now the properties of approximation in value space in this one control at a time context are not so clear as they are in the case of rollout. I have a paper that you can consult on value iteration involving multi-agent problems and approximation in value space. So we can discuss that at some time.
Yeah. Thank you so much. Yeah.
Okay. Okay, so let's go now into perfect state observation problems. And I'm going to start with an example. Remember, in perfect state information problems, there is some quantity that you would like to view as state, which summarizes all the information that it's a convenient state. On the other hand, you may not know that, and you may only have some measurements or some observations relating to this quantity of interest. In this example here, you have a car that wants to park in one of the M spots of a linear parking lot. So these circles here denote parking spaces that may be taken or they may be free. And the driver wants to park in one of these parking spaces within some time, okay? Within some time n. And he looks around for a cheap, for a parking space that has low cost, okay? There's some cost structure assumed here. Each parking space, let's say M, has a cost associated with it, C's of M. So upon reaching M, the driver looks first at whether the parking spot is empty or is taken. If it's taken, then it goes either to the left or to the right. That's the decision. However, if the parking spot is free, then he can go to the left or go to the right without parking, or he can choose to park at this cost C's of M. Now, if the driver had a map of the parking lot, okay, it was given to him a map of all the spaces and their status, and then at the beginning, and is given this information at the beginning of each stage, then that would be a problem of perfect state information. However, let's assume that the driver can only observe the free or taken status of only the spot that he's in. So he's at state M, he cannot observe the status of other parking spots except this particular spot. Moreover, even if he has seen some of the parking spaces to be free or to be taken, their status may change over time. At the next time step, the parking spot can change from free to taken or from taken to free with some probability. So the information that he has collected from previous observations is not reliable, it's not certain information. The status may have changed. So what would make sense here? We can estimate the status of the spots in some probabilistic sense. In other words, we may have a probability distribution of the state of the parking lot and the probability whether each individual state is free or taken. And we can update this probability distribution as we collect more information. We visit more spaces and take a measurement of whether they are free or taken. Now, is this a legitimate state? Well, the state should summarize all the information that's necessary for the purpose of future optimization. And I can argue that all the information that has been collected through visits to different parking spots can be summarized in this estimate of probability distribution. There's nothing else to know. If you think about it, that's it. This probability distribution is the only contains all the information that's necessary for the purpose of future optimization. Proving it, of course, is another story. You have to prove it mathematically, but intuitively it makes sense. It's also possible to use a different state, which is the set of all observations so far, the list of the status of all the parking spaces that he has visited and the time that this has happened. On the other hand, this state can expand over time, and for a large number of steps, it can become hard to deal with. So another possibility is to use as state the belief state, the conditional probabilities of the free taking status of all the spots. So this is a vector of probabilities that's maintained and updated at each time step, and is conditioned on all the observations so far. So with this new observation, this probability distribution is updated to some kind of estimator that the driver maintains and looks at this belief state and makes a decision of whether to park or not to park and whether to go right or left. So for example, this probability distribution says that likely there are quite a few free spots in this region, and this region here also contains spots of low parking cost. Then the driver can usefully take this into account and move in that direction. And similarly, this probabilistic map of the state of the status of the parking spots can guide fruitfully the decisions of the driver. So that's basically the context within which problems of partial state observation are formulated. We introduce a problem that has all the dynamic programming characteristics that we have discussed so far, including a system equation, control, stochastic disturbances. The state, however, of the system is the belief state, which we call BK. The belief state is a probabilistic estimate of the unknown state. It's the conditional probabilities of the different states given the observations obtained so far. The observations are this ZK plus 1. And the new belief state at time k plus 1 is obtained as a function of the current belief state, the control, and the observation that you have obtained at time k plus 1. This is a legitimate system of the type that we have been discussing, involving state control and disturbance. And also you can formulate a certain cost that depends on the current belief state and the control. So this is our new system now, and the state is the belief state, and then the controller observes this belief state and applies a control as a function of the belief state. So this is the type of reformulation. We're going to see in the future examples of this, but for the moment, we have gotten into the framework where we can apply our dynamic programming algorithm with perfect state information, because the controller knows the belief state, so it knows the state of the reformulated problem. And this dynamic programming algorithm is given by this form. The optimal cost of the tail subproblem at time k, given that we are at belief state bk, is obtained by minimizing overall controls, the cost of the first stage, plus the expected cost to go from the next belief state, but also with an expectation, because this quantity involves the unknown observation, the probabilistic observation that we have here. So that's the dynamic programming algorithm. This is the reformulation, but it's a much more complicated problem, because the belief state is something much more complicated than the state that you started from. There's a difference between states and probability distributions over states. It's a much more complicated object, and doing an exact dynamic programming computation is simply out of the question. It's impossible, except for some entirely trivial and contrived problems. You cannot do exact computations with exact dynamic programming. However, reinforcement learning allows you to deal with problems like that by introducing cost function approximation, by introducing rollout, by introducing approximate policy iteration, and all that. This, of course, is very complicated because of the more complicated nature of the belief space, but it has been done and it's possible, and the methods that we're going to be discussing are suitable for this purpose. So that's all I'm going to say for the moment for partial state observation problems. They involve various formulation, a belief estimator, and a reformulated cost, and some kind of approximation to the dynamic programming algorithm, likely using approximation in value space and quite a bit of computation. So, are there any questions? This is our last topic. Okay, so let's go to the next lecture. We'll discuss adaptive and model predictive control within the context of approximation in value space, Newton's method, and rollout, approximate policy iteration, and the like. Then we're going to go into more general problems. We dealt with one-step or multi-step approximation in value space in the context of alpha 0 in general, and in more quantitative terms and with visualization in connections with Newton's method for the case of a linear quadratic problem. Now we're going to go to more general problems involving finite and infinite horizon. And we're going to the extent that we're going to give visualizations similar to the Newton visualizations that we gave in this lecture, but for more general Bellman operations, more general Bellman equations. And we are going to go into a more in-depth discussion of rollout, starting with deterministic problems, and discuss various variants and some of the properties of the variants. There is another homework. Your first homework is due today. There's another homework due in 1 week, which is exercise 1.2 of your class notes. The class notes have been updated, and they include now a new exercise 1.2. And this is the subject of your homework. It would be useful to do some advanced reading and watching. There are a couple of video lectures that are relevant to the next lecture. And this is also a good time to watch the video lecture that summarizes one of your textbooks. This is the new textbook that I am now finalizing, and it involves a lot of these visualizations and the connections with Newton's method. And there's an overview lecture at YouTube, and it would be a good time to watch that in preparation for the next lecture. So are there any questions? Okay, we're expecting your homeworks, and good luck with the next homework. See you next week.